be talking about Rowhammer.js, which is a JavaScript implementation of the Rowhammer attack. Out of curiosity, how many of you have heard of the original Rowhammer attack? Okay, cool. So Rowhammer is a technique that you can use through software to take advantage of a hardware flaw in memory. The flaw is that by accessing memory, you can flip bits in portions of memory that you don't control. By doing that, you can, by doing that, one of the attacks that's taking place is that because you can flip bits that you don't control, the operating system isn't in the way because this is done through hardware. You can use that to take root access for a machine that you can only run code on. Another one from a long time ago was breaking out of a JVM just by flipping random bits. And then the one that I'm going to be talking about is breaking out of a browser, taking control of the machine that was running that browser purely by running JavaScript. So this is a problem with memory. The good news is that only one kind of memory is affected. The bad news is that it's the kind that you're using in your machine. So if you have like 8 gigs, 16 gigs of memory on your machine, whatever, that's going to be a type of memory called DRAM, and that's vulnerable to Rowhammer. One of the early papers that talked about Rowhammer, they tested 129 different memory modules, and they found that 110 of them were affected by this flaw. Another kind of memory that you can have is called SRAM. That's the kind that's used in your CPU cache, and that kind isn't vulnerable. So DRAM, the way that it works is that it stores your data in a capacitor. A capacitor is kind of like a small rechargeable battery, and what you could do is you could charge the capacitor up and say that that would represent a 1, and if you discharge the capacitor, that would represent a 0. So what you can do is you can store that bit of memory in a capacitor, and then by using a transistor, if you apply power to that, you can connect it to the rest of kind of the machinery for the memory. If that capacitor was charged, that charge would go through. You have a little sensor in there to check to see if it was charged or not. And then you put that into a latch, which is basically kind of a buffer for that 1-bit memory. The problem is that a capacitor, at least the really small ones that you're using for memory, they can only store a really small charge. So it's kind of once you connect it, that one-time charge goes out, so you have to capture it in this little buffer to keep track of it. That was just a 1-bit one. In reality, on the right, you would have them in a row, in columns. You would have, this is a 4x4 memory cell. It's basically the same as the other one, except that a little bit of the machinery is shared, like the latch for storing the data, that sense amplifier for comparing it. And then what you do is you can read or write a row at a time. One problem with using a capacitor for memory is that because it's so small, the charge will decay over time. Or actually, it's because there can be internal resistance in the capacitor where it's not perfect. It will kind of leak a little bit out. The transistor isn't perfectly resistant, so it will leak a little bit out there. So it will kind of lose the charge. If you stored 1 in it, over time, it would degrade and turn into a 0. And that happens on a pretty small time scale. With the capacitors that you would use in memory, it would happen on the order of like seconds to a fraction of a second. So that's why if you've ever looked at your memory, you might see that it has a refresh rate of 64 milliseconds or something like that. That means that every 64 milliseconds, it's reading out the value in that capacitor, reading it into the row buffer at the bottom, and then writing it back out into the capacitor again to refresh it. Now, the problem that happens that Rowhammer exploits is that when you read from a row, when you read that capacitor, there's some interference that goes on that can affect rows that are nearby to that row, mostly the adjacent rows, the one above and below that. What it causes is that when you read a row, it can cause the charge in those adjacent rows to decay faster than they should. So if you had written a 1 into it, it could decay and it would become a 0. Now you're kind of you're racing against the refresh rate here, where if that charge is decaying and then you refresh the row, if you catch it in time, then it's still going to be okay. It's still going to write back a 1 or write back a 0 is what it was. But if it takes too long for it to refresh, if that decay changes the bit enough, then it will cause a bit flip, and you've modified a bit that was just adjacent to the row that you had. Actually, any questions about how memory or any of this stuff works so far? And feel free to interrupt me anytime. No? Okay. So this is the original Rowhammer attack, at least the part to exhibit Rowhammer. This is some assembly code. The first bit is saying, so lines 2 and 3, what it's saying is just read the memory at address X, put it into a register, and what we're doing is reading from memory with that. Now, we need a little bit of other things here, because if we just repeatedly read from one address, what's going to happen is that it's going to be stored in that buffer. Let's try the laser pointer. It works. It's going to be stored in that row buffer at the bottom, and you're not going to have the capacitor discharge, which is what causes whatever interference that happened with the other ones. You're just going to be reading from that row buffer, and that row buffer is different than this capacitor thing. So you can repeatedly read from it, and there's no problem. So that was one thing you have to do. The other thing that you have to do is that your CPU will cache memory access that you have, but we can work around that. What we want to do is we want to actually access the underlying memory. Luckily, there's a way that we can do that, which is the CL flush instruction. It stands for cache line flush. What you can do is you can tell the CPU to flush out whatever cache it has for that memory address, and then it will make sure that it will go to the underlying memory to actually access it. And that's at that point where that row buffer problem comes into play. And to deal with that, all you have to do is you have to access 2 different memory locations in that same chip. So the CL flush will get around the CPU cache, and then accessing 2 different memory locations works around the row buffer. The mfence instruction is just to prevent operation reordering, and so later papers have said that you don't even need that, so you can ignore that for now. But when you run this code, what happens is that memory addresses that are adjacent to X, or Y in this case, they have a chance of becoming flipped. If you access it enough times, and if the conditions are right, you can flip bits in memory in something that you don't own. Yep?
Does it always only go from 1 to 0, or can it go the other way?
So does it only go from 1 to 0, or can it go the other way? It almost always goes from 1 to 0. So actually, the way it almost always goes is from charged to discharged. But the thing is that some memory modules encode a 1 as charged, but some of them encode a 1 as discharged. And there are even others that alternate like different blocks, where some of them are like odd numbered blocks or whatever are charged as 1, and the other way for other ones. But there were very, very few cases where it could actually go either way depending on what cell. Although it's unclear if that was just kind of like a manufacturing defect that was different from this specific thing. Yep.
Do the order here that you've got move X and then move Y and then CL flush X and then CL flush Y, is that somehow I didn't quite get the point that you were making. Like, I understand the CPU cache and the CL flush gets around that.
Yeah.
But when you do move X to EAX, is it moving the stuff to the row cache? And then if so, doesn't the second move instruction already do that by doing the second CL flush?
Okay, the move instruction, we don't actually care where we put it. In this case, we're putting it in the register EAX and EBX. We don't care where we put it. All we care about is hitting memory. And so the CL flush it instruction is what makes sure that we bypass the CPU cache, or that we clear it first, so that the request goes to the underlying memory module. And then the 2 different addresses are making sure that you fill the row buffer, that the memory chip will fill the row buffer with one of them and then with the other. if you only did one of them, like move X and then CL flush X, it could be fulfilled just by the row buffer on the memory chip, even though it would go to the memory chip.
That it's going to actually be get flushed the row buffer if it was only one. So this is
Yeah. There's another question. Yep.
Does the row buffer in the memory bank have any kind of associativity? And the question I guess is that does it matter what addresses are X and Y? Do you have a relationship between them? Or are they just two random addresses? Do they have to be the same bank, different banks?
Yep. Good point. The two addresses X and Y, they do have to be in the same bank. That's the unit of kind of sharedness of the row buffer. So that they do have to be in the same bank. They can't just be random addresses.
And physically the memory, what's the size? What's the usual size of the bank? So am I reading something in, like for example within a 4K page region, or am I reading something that could completely totally different parts of memory?
I don't know the size of a bank, but I think it's on the order of like megabytes. So it's not like a regularly tiny unit. It's big enough that you could have many pages allocated in that if you're using 4K pages.
So as long as I am relatively well aligned and not inside the same cache line, because if I'm inside the cache line, I think the second group will never, the first move would cache both, right?
Yeah. So I didn't mention, but these addresses should be different cache lines. Like
Yeah.
the cache line is pretty small though, like 64 bytes ish. Yeah, that's right. As long as they're outside the cache line, but relatively close, but you know. Yeah.
So that bank only has one bit of buffer in its row buffer?
The bank, it has more than one. It has one row buffer. A row is just a group of like 2,000-ish
So
bits.
X and Y need to be in different rows in the same bank.
Different rows in the same bank, yeah. Actually, yeah, sorry, it's, I said something about cache lines before. It's different rows in the same bank.
And a cache is never going to span two banks, is that the idea? When you grab a little more memory than you need, you always grab a piece of
Sorry, can you repeat that?
So we access a memory address, the CPU grabs a little more than it needs, that's your cache line. Right?
Yep.
That's always going to come from a single row. That cache line will always fit into a row.
Yeah, the row is, as far as I know, a row in memory is going to be bigger than the cache line. Although maybe they'll be approximately the same size, but it shouldn't be.
But like if you
smaller.
grab a byte off the end of a row, it's not going to cache the end of that row at the beginning of the next row.
I think your CPU probably wouldn't do that because then it would have to do two different memory accesses. So it would probably cache the row that it's in. No, sorry, the cache line that it's in, it would kind of move to the front of that and grab that. Any more questions? Okay. So next part is we can flip a bit that is kind of adjacent to one that we control. How can you use this? One way is if you just kind of try to get lucky and maybe the bit that you flip is the one that says that, you know, instead of being not root, you are root, or some file that, you know, you shouldn't be able to access, now you can, and you can use that to get root. But there are lots and lots of bits in memory and not that many that will give you root access. So ideally we want something better. Something where we have a bit more, a bit higher probability of gaining root access. To do that, we have to look a bit at how memory is laid out and virtual memory in particular. So processes don't have addresses that point to your physical memory. That would be actual, you know, the actual underlying addresses in the memory chips. Instead, you get a virtual address space. And then whenever you access things in your virtual address space, they get converted by the CPU into the physical address space using a page table entry. So you have a little bit of indirection here. So when you try to access partway through, you know, that one there, you look up the page table entry that corresponds to it, and then you go to the corresponding offset in physical memory. Now, what we can do is try to fill up memory. We have lots and lots of page table entries. We have lots of physical memory that we're using up. Actually, part of this, some details from the original Rowhammer attack is that it can be a little bit hard to intersperse your memory with page table entries, but it is possible. Just take my word for now and follow along. Because remember that we can only do it to adjacent memory. We can only flip bits in adjacent memory, not just random memory anywhere in the address space. But if we do have some that are adjacent to a page table entry, what we can do is we can Rowhammer one of these ones. If we get lucky, we'll get a bit flip in the physical address portion of the page table entry. And the page table entry itself is not very big, so most of the bits are taken up by the physical address itself. So that's a pretty high probability of getting it. And then the other part of getting lucky is if that page table entry, when it flips the physical address, if that then points to a block of memory that contains another page table entry that we control. If we have this set up, then we have another bit of memory where we can read and write to the physical memory address of one of our page tables. So using the first one up here, we can write the page table entry points to here. We can change that physical address to instead point to whatever page we want. We can point to our own memory, or we can point to another process's memory, or kernel memory, anywhere in physical address space we can point it to. And then we can read and write to that. And using that, we can get root access with a more straightforward exploit than just hoping for luck. Robert, you have a question?
I think that you very lost me at some point, but how do you actually find the PTs again? Or you just like bombing all sorts of memory that you have in the process?
Yeah, you're not trying to find them. You are bombing all sorts of memory and just hoping for it. Actually, one part that I left out is that these bit flips tend to be fairly reproducible, or at least you can try to find some. So actually, yeah, first phase of the attack might be back here. We would allocate memory. We would find a bit flip that we could reproduce. Then we would free the memory of the victim cell, the part that would actually be flipped. And then we do a bunch of other work to get a page table entry to go into there. And then when you do it, you kind of know where you're expecting it to go. And so it's not as big a search space, but it is basically just like do it and then try to figure out if it's pointing somewhere useful.
Does it happen in low memory conditions where you usually have to allocate a lot of memory in the machine? That just becomes statistically a problem.
Yeah, that's exactly it. That in order to get them to fragment, at least in the original attack at Black Hat that they presented, you have to have low memory conditions in order to get to really fragment the page table like that. But if you're lucky, you could get it without doing that, just because you might have one block of memory that's adjacent to a bunch of page table entries. Any questions about exploiting it? Okay, cool. Now, the paper that this is about is Rowhammer.js. The key thing that we had with the assembly code before was the ability to flush out the memory address or the cache entry from our CPU cache, so that when we read it later on, it would actually hit memory. The problem is that in JavaScript, you don't have a CL flush instruction. We have to come up with some way of doing it. So we have some target memory address. We want to do reads there and have it actually hit the underlying memory. One of the ways that we can do it is access so much other memory that you clear out every entry in the CPU cache, and then when you access this other one, it'll hit the underlying memory. The problem is that, so you access like the full size of the cache, but you have CPU caches that are, I don't know, 60 megs, 32 megs. And remember that you're racing against the refresh rate. So you have to access the underlying memory, that address key, enough times within one refresh rate, usually like 64 milliseconds or something like that. Enough so that it will flip a bit. So if you're reading a ton of other memory in between, you're not going to be able to do it fast enough. You're not going to be able to hit that target address enough times to get it to flip. So you have to come up with a better way of doing it, some way faster. To do that, we have to look at how your CPU cache works. Your CPU cache is a giant block of memory. You can think of it like just a fixed size array that you have. And then when you access elements in memory, you put them in the cache. But the question is, how do you put them in the cache? An easy way would be if you access memory, you put it anywhere in this array, anywhere in this cache, but then when it comes time to read from your cache, you have to read from every slot to figure out if it was in the cache. So that would take either a long time, or you could do some hardware stuff where you search in parallel, but it would be a lot of hardware to do. Either way, it's a bad idea. A kind of the opposite approach to that is that anytime you're reading memory, when you want to put it in your cache, you do something like hash the address, and that will map it to one slot that you can put it in. You could do something like take kind of some of the lower bits of the address, and that would always be the slot that you're putting it in. The problem is that if you have even 2 memory addresses that map to the same slot, and they're really hot, and you're accessing them a lot of the time, then you're going to kick them out repeatedly, and you're going to have bad performance. So that's a bad idea too. The ideal way is somewhere in the middle there, where any given address has a few different slots that it could map to. You have some function, different hash functions, or whatever, some mapping from the address, the different slots that it could be, and then you put it in one of those slots. A typical way is, even though you have 60 megs, 32 megs, you can store thousands of entries. Usually, an address can only map to something like 8 or 16, or the number of cores, or number of cores times 2 or 4, or whatever. Only a few slots. So if you could figure out a bunch of addresses that map to the same slot, those are called congruent addresses. If you could find enough of those, then just by accessing those few addresses, you'll kick out your target address from that slot if it was congruent to those addresses too. The problem with doing that is that a lot of that stuff is undocumented or proprietary, so the mapping function of an address to what slots it goes into, those usually aren't documented. And even beyond that, when you have a choice of 4 slots, you can pick any one of those to evict. And there are better strategies for doing that. You can pick ones that are not accessed very often, or which ones of the ones that aren't accessed very often should you kick out. And usually those functions are proprietary as well. So we want a way, a few of those have been kind of reverse engineered as well. So you could pick a few CPUs and figure it out, but that would be really annoying to do for all of the kinds of CPUs. Ideally, we want some way of figuring out kind of a cache eviction strategy that doesn't really depend on what that address function is or what their eviction strategy is. And that's one of the big things that they created in the paper. So this is pseudocode. Actually, they released a new version of the paper just a few weeks ago. It's probably the one that you read if you read the paper. They had an older version where they focused more on this part. So on the right-hand side is the pseudocode that they came up with, that they ended up implementing in JavaScript, and a pseudocode on the left of my explanation. So remember, the goal is we want to come up with a bunch of addresses to access, that when we do that, we will kick out a target address from the cache. So that then we can hit that address, read from it, and ideally execute this Rowhammer attack. So what we do is, to start with in JavaScript, you can just you can create a large array of elements, and then to access a given address, you're just picking an index in that array, reading from that index. So all that address stuff is just reading from an index in an array. What we start with is we want to keep on, yeah, question?
Sorry, I'm trying to picture it. So why are we trying to flush the CPU cache? We're trying to access point in the memory enough times to cause a bit further milliseconds.
Yeah.
Just connect the dots between the DRAM cell and the CPU cache.
When you access a memory address, if it's in the CPU cache, you're not going to hit the DRAM cell. Instead, you're going to get it from cache. Pardon me?
It's because we don't have CL flush.
Yeah, before we were able to get around that by doing CL flush, so that every time we told the CPU to access this memory, it would go to the underlying DRAM cell. But without that instruction, we have to do kind of a workaround way of, a roundabout way of flushing the cache. And the way that we can do that is by trying to access a bunch of different memory locations that would map to the same slots that our target memory address would map to in the cache. Make sense?
That's really round, yeah.
Okay, cool. So that's what we do. We have a list of memory addresses that we're going to access before we access our target memory address. And what we do is initially, if we just access our target memory address P, it's going to be cached. If we add one address that we try to access before, it's going to be cached. We keep on adding more until we get to the point where it isn't cached. And actually, this cache method, you can't just in JavaScript ask if a memory address is cached. The way that they do it is with kind of a mild form of a timing attack, which is taking advantage of the main reason why you have the CPU cache, which is to speed up access. So the way that you can determine if a memory address is cached is you access it and you see how long it took. If it didn't take very long, it was cached. If it took a while, it wasn't cached. The issue with that is that that's kind of a noisy measure, like maybe it took a while because there was a GC pause or a context switch or whatever. But the workaround for that is just do it a bunch of times, access these memory addresses that we built up, and then access the other one and time it. And even if you have a low resolution clock, you can still average it out and figure out, was it cached, yes or no. And you can kind of increase the number of attempts that you do to get a better resolution or a better idea of whether or not it's cached. Yep.
And when you do that, if you get a number where, it wasn't cached because it took a long time, but wouldn't it be cached by now?
The first access though, so we have a list of memory addresses that we're gonna check, that we're gonna read, and hopefully evict the slot that our target would be in. We read all of those, and then we check the target one, timing it. And that loop that I'm talking about is not looping over checking the last one, it's the whole thing. It's read all those addresses, and then read the target. And then try again, read all those addresses, then read the target. And timing the target the last time and averaging out that time. And through that, you can figure out whether or not it was actually cached. So with this, now you keep on adding addresses until it's not cached. You're going to end up with a bunch of ones that are congruent to that one target address, but lots and lots of ones that aren't, that you don't care about. So, yeah.
How many times do you have to access a particular address and make sure that you get do they have a feedback?
Yeah, how many times do you have to access it to get a bit flip? Something like hundreds of thousands of times within a refresh cycle. So there are some, if you're doing the CL flush one, you can get it as low as, I think, 200,000 times is the lowest that they saw, at least on average, within 64 milliseconds to get it to flip. And then some of these other ones, you have to access it more often.
So 100 needs essentially take less than 100 microseconds to achieve the
Yeah. Yeah, this whole thing about reading these addresses, you have to make sure that it takes a small enough amount of time that you can do it hundreds of thousands of times within 64 milliseconds. Another question?
What happens if insert R into eviction list? I mean, if you remove R, what happens if does that insert R into eviction?
Sorry, this one or the next slide? Okay, the eviction list is the list of memory addresses that we're going to access in order to try to evict our target one, P, from the cache. So we keep on adding memory addresses, which are just indexes into our array that we're going to read from, hopefully trying to evict that item from the cache.
So, I know nearly nothing about JavaScript. I would suppose that JavaScript supports some form of threading.
JavaScript and threading. JavaScript is basically single-threaded, at least from your perspective.
Yes, it was
Web workers.
Pardon?
Web workers, but yeah.
Web workers? Sure.
because I was wondering if you could do that with the threading, like if it supports threading, even if it doesn't support things like SE11 and CL flush.
I think a lot of CPUs will split the cache by 4. So if you can get
No, but
something
you can
to
pin,
thread,
you can very likely pin the thread.
not in a JavaScript.
Yeah, you can't pin a thread in JavaScript, so that idea is out. And what you care about is probably you mostly care about the single threaded access, although I guess you could do a multi-threaded one. And about the CPU cache, a lot of them do share, like they have their own cache for part of it. They usually have a shared cache that all of them have. But the nice thing is that this attack is completely agnostic to any of that stuff. All it cares about is getting it out of the cache. So we've added a bunch of addresses until we have so many that we can access that it will evict P. Next step is we've got a bunch of them that are congruent to each other, but we probably have a ton that aren't. So what we do is we just go through and keep on replacing addresses one by one with other addresses from the list, and then trying it again, seeing if it's still cached. So we reduce that kind of the set of addresses, or it's a list here.
So the L2 and L3 doesn't follow the same here. Can you actually guarantee this, you're getting stuff out of L3?
Yeah, that's actually the goal. You have to get it out of L3 in order to hit RAM. So yeah, this will get it out of L3. Yep.
Can you tell us what the size of the list is that we're expecting at the end of step 1 and at the end of step 2?
I don't know the size of the expected list. My random guess, it would probably be like hundreds of addresses in the first one. I can tell you that the runtime of this whole algorithm, it varies depending on how careful you want to be in that cache method, how many times you want to iterate over it, which is basically how certain you want to be that you're evicting it, because the eviction rate is part of what you care about in actually executing Rowhammer. If you want to be really certain, it takes about an hour. But that's kind of like the magnitude. If you want to be less certain, you can do it with less than an hour, but it wouldn't take more than an hour to do this kind of stuff. Another question?
Do you know if they're using the high performance clock in the actual JavaScript for this?
I don't know, but I would bet they would use whatever highest resolution clock they have. But again, with this kind of timing attack, you can use a lower resolution clock as long as it's still accurate or whatever. Sometimes you think, yeah, like, and because you're repeating it multiple times, even if the resolution they expose to you isn't very good, you can still do that kind of thing. And I remember in the newer version of the paper, they did mention that they were using whatever the newest standard was, which I think was a lower resolution than normal.
Lower than normal?
I thought. Otherwise, I don't know why they would be mentioning that.
There's a new clock that gives you approximately microsecond, rather than the old one that was approximately millisecond.
Okay. It might be the microsecond one, but even with the millisecond one, unless you're adding noise to it, and in a way that was deliberately trying to mess with you, you would still be able to use a lower resolution clock to determine this kind of stuff. Any other questions? Cool. So we now reduce the list, reducing the number of addresses that we're trying to access, even though we keep the same number of memory accesses overall. So we're just replacing, if we were accessing 100 different memory addresses to begin with, we're replacing them one by one. We'll still access memory 100 times, partially because we add them twice, it would be 200 times, but still the same number of times. And we keep track of whether or not it's cached to do the right thing. And then in the last step, we remove the memory addresses, or the accesses completely. So what we should have by the end is only a bunch of basically congruent memory addresses to our target, and then we reduce how many times we're accessing them. And in this part, you can't just access everything once, because that isn't optimal for a lot of the eviction strategies that CPs have, because they might wait for you to access it twice in a row, or maybe twice with a gap in between. But this technique still finds those kinds of, it still deals with that kind of eviction strategy. So, actually, at last check, any questions about how this part works? Yep.
So I'm trying to kind of visualize it. So you mentioned how the scripts would create some huge fixed size array in order to allocate a bunch of memory. And then this algorithm is to figure out the cache collisions, right? To figure out some addresses that are gonna collide and be able to help with cache eviction.
Yep.
So when you say here you're adding random addresses, is this in a new list? In the JavaScript, would it be representing addresses as integer indexes into that array?
Indexes into array, yeah.
And when it says add random addresses until target address isn't cached, is it like just starting at, is it just starting at like 0 and then trying to find some cache eviction addresses for address 0 and then going up to, is it trying to find eviction
So I guess your
strategies?
question is more about how reusable is this for a different block of memory? Is that what you're getting at?
I'm curious if it's trying to do it for all addresses in memory or just some that it is identified as desirable. That's one question I have.
Okay, so is it trying to do it for all addresses or just the desirable ones? I'm not exactly sure, but the ones that are desirable are going to be kind of at the edge of the memory you control, because then it's going to be
Right.
some other ones. But
So
a lot of this should be reusable for basically any block of memory, because most CPUs just look at the lower address bits for determining how they should be putting these slots in.
Okay.
If you have really different high bits, it's going to be a different bank. So it's the low bits that you care about. So it means
So
that if
this
you have
this
different
algorithm, as described, is for when you have a single target address, right?
yeah, but
Okay.
you should be able to just kind of offset them, I believe.
Okay. Cool.
So it is reusable for other addresses. You're not doing 1 hour's worth of work just to find how to evict one specific
Okay.
memory address.
And-
You can reuse it. No.
So then okay.
That's the initial part, but because a lot of the logic is going to be the same, just depending on the low address bits, you can allocate a completely different 2 meg array, and the low bits are going to be mostly the same, and so you can just transition this up, like it'll be the similar offsets within it.
So when you're talking here about like you add random addresses, so is this into like some new list of like this is
It's a list of indexes, yeah.
yeah, okay. So you have some other list of indexes. You're adding like true like pseudo random, like you just pick random indexes from the array and like
Yep.
like hoping to find ones that work. And the part that I understand the least is like I think step 2, replace all instances of a random address with other addresses in the list.
Okay, those are random addresses within the list. So we build up this list of a bunch of different memory addresses that when we access them in sequence, followed by our target one, it will be evicted.
Okay, so we've already found those. Okay, we've already
Yeah.
found good addresses that are colliding.
We found all of our good ones, plus we found a bunch of useless ones that don't actually matter, just because we've been adding random ones until it's not cached.
Oh,
Then the
okay.
next step is
Got it.
get rid of all these ones that don't matter by changing
okay.
them to other ones and seeing if it will still be not cached.
Okay. Okay.
Any other questions? Yeah.
So what's your final eviction list E? Can you swap P with a value in E and that works since they're all congruent?
Can you swap P with any value in E?
So they're all congruent.
I think the answer is maybe.
So if you take some other address in T, it's going to have some things that it hashes, right?
Yeah, and then
Those aren't necessarily the same things that P hashes, but they overlap in at least one spot.
So I think it might work, but it might not. But in any case, you can probably like shift all those addresses up by 1 or down by 1 and still work. I'm not sure exactly how they did that transition. I didn't look through it, but I do know that once you have this this eviction set, that then they reuse it somehow to evict whatever other addresses they want.
With the idea that the CPU is only hashing the low bits of the address space.
Yep.
So if you figure out where in physical memory these blocks are relative to each other,
Yeah, but also remember that the high bits, it's not going to bother hashing because it's going to be, actually wait, I guess they could matter. So it could involve the high bits, but I think that in practice they tend not to. Yeah. So, I touched a little bit on this before, but can you actually use this to take over? So this cache eviction strategy, I mentioned before that it can take up to an hour to do that. They do have a different version of it that they talked about in the second version of the paper. Actually, what they focused on more was coming up with, that they have this offline processing step where they come up with a strategy that will find this eviction set quickly. What they do is they do a pre-processing step per CPU. So they kind of attack the CPU, figure out a way of characterizing how you should be coming up with these accesses, like how many different memory addresses you need, how many times you should be accessing them, that kind of thing. With that offline step, which takes hours, but it doesn't really matter, you can characterize the CPU so that in a few seconds, you can come up with a strategy that will work for it.
Based on like CPU's technique or whatever the undocumented stuff.
Yep, exactly.
is doing.
Yeah, it's based on how they do their addressing function and how big the cache is, how many ways, all that kind of stuff. Now the other part is that you have to find a useful repeatable bit flip, which is a bit flip that is kind of on the edge of memory. If you have a block of memory and you've got a bit flip in the middle, that doesn't matter because you can't get other processes' data to be in the middle of your bit flip. You can't get a page table entry in there, so it has to be always at the edge. And for that, they said that it can take several hours to be able to do that. Yep.
But if we over the edge, right?
Yep, yeah, it's over the edge. It's you. How do you detect it? Okay, so what you tend to do is you do it in memory that you control initially, and then you release that memory later on. So you know that it's on the barrier of what the OS would do for a page, and you can actually, they do another timing attack to find those page barriers, because it has to do with like you access all the memory in one page, and when you go to a new page, there's a little bit of a delay for the first byte that you hit. So you can time attack to find that. But if you have a whole block, then you can find where those barriers are. You find a repeatable bit flip, and then they actually didn't talk too much about how they get like page table entries to be in the middle. And in their GitHub code, they don't release the exploit code for that. They only release the rowhammering portion for it. So, somewhat practical if you are doing what they call the assumption-based attack, where they do that offline step of figuring out how to attack a specific CPU. Then it can be just a few seconds to begin rowhammering. And then that other part about finding a useful one, that's basically luck. It could happen really quickly, could take a long time. So, somewhat practical, somewhat impractical, you can decide. What can you do about it? How can you defeat this? How can you protect yourself from it? One of the ways that some memory manufacturers or motherboard manufacturers have done is just increase the refresh rate. If you make the refresh rate fast enough, then you can't access memory enough times in between the refresh rate to get it to bit flip. And that can mostly deal with this. One of the downsides is that you don't want to increase it too much, and actually you want to make the rate as slow as possible because it's better for efficiency. Refreshing your memory takes energy, and it's also time that it is doing other things, and it can't be servicing your reads or your writes. So that works, but you don't want to do it. Another one that you might want to rely on is error correcting memory. Problem is that it just decreases the probability. In the original Rowhammer paper, they had tons and tons of 1-bit errors, but they also had 2-bit errors. They had a few, or actually quite a bit less, 3-bit errors, and even a few 4-bit errors. Most ECC RAM will detect 1-bit error, will correct 1-bit error and detect 2-bit errors, but they had 3-bit and 4-bit errors too. So decreases the probability, but doesn't completely solve it. And it wouldn't be very good to increase the parity enough to catch all that. That wouldn't be the most efficient way of doing it.
What do you measure in terms of efficiency there, like the overhead of it?
Sorry, in the first one? For ECC, the efficiency is just you have to add more bits for parity, so you have less for data.
Right.
If you were going to add those parity bits, instead of that machinery, you can do the third technique.
Okay, at the same cost or lower cost
in terms of the cost of the cell or that kind of thing. The other one is basically just directly avoid this attack, which is the attack is if you read from memory enough times within a refresh rate, then you can come for bit flips. What you do is you keep track of how many times you've read, probably not an individual row, because that would be a lot of memory, but a block of rows. If you've read from a certain block of rows, just refresh all of them and kind of the adjacent ones too. And a similar technique is the probabilistic one, which is anytime you read from a row, you have a certain probability of just forcing a refresh of the adjacent rows. And then that's less machinery than kind of adding enough error correcting bits to deal with these bit flips.
But it's okay, and that's based on the attack vector that this manifests itself only when you read it again within a refresh window. So by tracking that, when it passes a threshold or something, the CPU and the hardware can perhaps intervene.
Yeah.
Okay.
But this would be on the memory chip itself.
Yeah, it's a hardware change. So that this directly solves the problem, but it requires a hardware change so it doesn't fix all the existing memory that you have running now. Probably the coolest one is the last one, which is a software-based technique for defending against it. And they take advantage of when you are reading directly from memory, that is a cache miss for the CPU. The CPU has performance counters that measure how many cache misses it has. So what they do is they have a bit of kernel code, they monitor those performance metrics to see how many cache misses are we having. If we have a lot of cache misses, then they enable a second level of monitoring, which is watching what addresses are having the cache misses. And then if they're really localized, then you assume that the attack is taking place, and you can just refresh the rows that are related or that are adjacent to the ones that seem to be attacked. And that works, at least for all of the attacks out right now. But it has, they said, about a 1% performance drag. And the other thing that I didn't like is that they almost tuned it to the attacks that they have right now, where they said the fastest attack that you can do takes whatever it was, 20 milliseconds. And so they monitor that initial CPU cache miss metric for 10 milliseconds, and then if it's enough, then they have this much time to do the other one. So if there were faster attacks, then they would have to kind of retune that, and it would have an even bigger performance impact. Yeah.
And I think, well, you see that, right, where the ECC is a robust thing, which is just, it's providing you good properties of just the memory itself. It's not looking at a particular attack vector of that you need particular access.
Yep, the ECC is more general.
And go to this third one, which is for a particular attack vector as opposed to particular attacks or attacks that you know. And then you go to the software one, which is even more specialized and saying, okay, these set of attacks that we know, well, now we can also correct.
Yeah, that's a good point, that they are kind of ordered by, accidentally ordered by how specific they are. Yeah. And yeah, some related stuff. The only one I'll call out is the the second point there. There's some code on GitHub from Google where you can compile it and check your machine to see if it's vulnerable to Rowhammer. You just run it, and it'll keep on going until it finds a bit flip. So, run it for a few hours and kill it if it doesn't find one, and you'll be safe. Yeah. So, that's what I have. Thanks for listening. Any final questions? Yep.
So when you're checking your machine, the answer to whether or not it's vulnerable depends on the physical properties of your memory chips. Is that true?
Yes, it depends on the physical property and also on your refresh rate. So that was kind of the workaround that some of the manufacturers took, of just increase the refresh rate. So it's also dependent on your BIOS settings.
But even if I know that I have a particular type of RAM with a particular refresh rate, like I know what the chip is, it's not like I can look it up and see, okay, you're safe.
No, I think you could probably.
It depends on the CPU too, though, because the paper said that newer CPUs have way different eviction policies that they haven't had than the new Skylines. So like you could use the old RAM, and it might be vulnerable on like Sandy Bridge.
Okay, yeah, I can see it depending on the CPU, how well it caches it, or what strategy you use to cache it.
Are there current sort of CPU or memory combinations which are actually safe as opposed to ones for which attacks are not been? It seems to be a fairly general attack.
Always buy the newest stuff.
Well, no. I mean, but I think that there's been a difference in. There's a reason that they haven't documented these eviction policies and stuff, and part of that has been, part of that is well documentation is hard, and there's lots of stuff that goes undocumented.
It's also they want it to be private.
Well, exactly, but that's privacy and protection by obfuscation
think that they're deliberately hiding their cache eviction strategies for the Rowhammer attack.
No,
I think it's
not
just part of like,
specifically, but just as a general policy of, okay, you know, we have this wall of, we should not release this as, you know, well, people should not need to know about it or things like that.
Yeah.
Right? As a general policy. And so my interpretation of when I became aware of the attack and also Rowhammer Js was more along the lines that like there hasn't been any chipset or like memory or thing combination which is like, yes, we are secure because we are employing ECC to a good enough extent, or that we already have implemented this patch in the kernel and this already there, the software one, which is again a sort of fixed set of attacks that they know of, right? Or that we've done any of this stuff. It can be done, can be implemented, but there's a good likelihood that you're at least vulnerable to the attack, even if it may not be manifested easily at present, right? Or
yeah, I think so. More questions?
Since it sounds like the timing's pretty tight, do you know if there's a minimum clock rate necessary to actually pull it off?
A minimum clock rate. I don't know, but it seems like most CPUs are fast enough to do it.
I think I saw that if they increase the clock rate 7-fold, so down under 10 milliseconds, that effectively would have to do the attack.
The clock rate or the refresh rate?
Sorry, the refresh.
The refresh rate, okay.
Yeah. But I
so by about an order of magnitude, a little bit less than that.
But I think there's like a power law of refresh rate of the higher your refresh rate, you have dramatically less time for conserving reads, or like dramatically more power. There's something like having the refresh rate more than doubles the power consumption.
Is this because of the threshold function that the roll-off
The
and
decay.
capacitor discharge things? Yeah.
Yeah, that is,
Is he talking about the refresh rate? Sorry, what the impression?
Yeah, that question was about the clock rate of the CPU.
That should
Yeah, so I-
happen.
Well, I mean, if your CPU is so slow,
Much higher. In any CPU that I've seen in my life, the latency for memory access is much higher than the CPU clocks. It's extreme.
yeah. Yeah, so you're probably not safe by underclocking. And actually, someone mentioned about like always use the newest thing. I think that a lot of older memory chips weren't vulnerable just because our manufacturing process was different. You could make capacitors that small, and so because of that, they were actually less vulnerable. So it was newer ones that became more vulnerable.
I'm still a little confused by this. Like checking your machine, you said it went through and tried to find a reliable bit that it could flip.
It just tried to find any bit that it could flip in the Rowhammer
And it's
test
an
one.
idea there that some of the capacitors in your memory chip might be vulnerable to this, but other capacitors won't.
It is usually that some are more vulnerable than others, yeah.
So it's almost a manufacturing defect that will affect some chips but not other chips.
Well, in a way, it's a manufacturing defect, but
It's a
in
manufacturing artifact at most, right?
Yeah.
We say, like this would just be, and there's going to be some distribution of these things.
I mean, when they tested the first one, when they tested, what was it, 129 and 110 different modules, those were completely different different SKUs. Like
All 129 were different chips.
it was from 3 different manufacturers, but different models of memory. So it wasn't that they grabbed like 129 of the same one and 110 were vulnerable. It was of 129 different memory modules, different like 3 different brands, and then yeah.
But in a way, you're kind of looking for a capacitor in there that's a little bit weaker, maybe leaks a little bit faster or something like that.
Yes, although I think their point was that those exist in like every memory module, or most, not every, but in many of them. Yep.
So basically, we need to do for an hour to find out defect, and there is a way to do it within minutes. So how come we can do this so fast? Previously, previous time, there was a. I mean, normally, if you find something, you need to run for hours to find something, and then there's another way.
Okay, that's these 2 different ones.
What is that something?
The assumption-based one is where they do an offline processing step where they pick a specific CPU and they come up with a way of figuring out how to do these memory accesses to evict the address from the cache.
They use a more specialized like approach, right? After having done that pre-processing, they can tune the attacks simply for that, and so basically whatever. That's why the first one is called the fallback, right? Because that's when you have software prior information as to the chipset, so it's a generic algorithm which is trying to figure this out.
Yep, that's exactly it. It's with their pre-processing step, they can know that, for example, we have to access, or we should access, 17 different memory locations, and we should do it in a pattern kind of like this. They still have a step where they're running through the different options to figure out what they should do, but it's a much more narrow search space. That's what their the assumption-based attack is. They do that offline processing step to figure out what assumptions they should make about the CPU to be able to evict it more quickly.
So basically, that assumption is have two factors. One is based on CPU. The other is kind of what kind of DRAM system you use.
The assumption one is just based on the kind of CPU. We only care about evicting from the cache for that one, and then we'll work with whatever memory.
The second part will take several hours on the slide. That's the part where you're actually trying to find the
So basically, the assumption is based on CPU. So basically, there should be some kind of or database or lookup table. If we for this particular CPU, I'm going to check this.
Yeah, you could make a database, and if you were actually doing this attack for real, what you would probably do is in the fallback attack, if you couldn't characterize their CPU, you would try to figure out what CPU they were using, do that offline processing step on their machine, and then report back results to you for future ones, and then you would build up that database of the most effective way of doing it per CPU. Yep.
Has this been found in the wild anywhere?
I don't know if it's been found in the wild anywhere. Anyone know? No? So, probably not, but maybe.
So how worried are you?
I checked my laptop, it was okay. You should probably be more worried about any services that you're using. They would be more likely to, like, if you hacked, I don't know, your bank or whatever, using this kind of thing. Because you only need code execution to do this. Like, if you can get any server that your bank is running to run any kind of code, or at least any code that can be compiled fast enough, like JavaScript, JCompiler, then you could potentially perform this kind of attack.
So guard against the attack by attacking the V8 or any other the compilers or JS, like let's slow down the JavaScript.
Yeah, slow it down. Actually, I think in this paper they proposed in your browser should try to Rowhammer you, and if it detects that it can, it should disable JavaScript to protect you.